All right, so this video is going to cover all the stuff that you need to know for your first quarter of calculus. Going to go over splits 5.5, well, 5.1 to 5.5. And this is going to cover extremas, Hospital's rule, or however you say it. I think that's how you write it. And then lastly, it's going to cover graphing. So, first things first, let's start off with extremas. Okay, so we got to start off with making a little graph here. Create this up. Make this two. I want is 7. 1, 2, 3, 4, 5, 6, 7. That worked. One. All right, and now I want this to go to about 4. 1, 2, 3, 4. That'll do. -2 will do. So for this one, we're going to start at 2. Go here. Let's say we peak this straight line, peak here. And we're going to go all the way down to 3. And then for 3, it's going to go to 5 about here. Now I want it to go here and then here. So now that we got that made, first things first, we want to find our global maxima and global minimas. This is going to be our easiest ones to identify, right? So we just look for what's our highest point and what's our lowest point, right? So for this one, we can obviously tell our global maximum, this maximum is going to be when x is equal to 4. It's going to have a y value of, not x is equal to 4, my bad. When x is equal to 2, it's going to have a y value of 4. Equal to 4, and then we're going to have a global minimum. Let's see here. When x is equal to 5, 2, and x is equal to 5, 2, 6. And then this is going to give a value of, what was it, -2? Right. Now we can start getting to some more interesting things. First, let's evaluate what's going on. It'll be highlighted. This section right here from 0 to 1. So we can say locally, if we really zoom in here, that from 0 to 1, this is going to be a local minimum. Local minimum when x is equal to 0, comma 1. Now, here's where it gets interesting. From all points from 0 to 1, but not including 1, this can also be considered a local maximum. Because say we're at, let me swap colors here. Say we're at this point right here. For something to be considered a local maximum, right? That means there has to be nothing else below it, right? So if we look here, if we're going further this way, nothing's below it. We go this way, nothing's below it either, right? But the same thing can be said about being a local minimum, right? Because nothing's above it either. So it can also be considered a local maximum or local minimum, right? But why we don't include the point 1 is because if you go a little bit, solve this here, if you go a little bit this way, all of a sudden your function is now increasing, right? But of course, if you go a little bit this way, you could also say it's maximum, right? But since we're looking locally right here, it can only be considered a minimum at that point. So, swapping back to white, we have a local maximum when x is equal to 0, including 0, but not including 1 because of all the points we just talked about there. And then we can go over a nice little target point here. Let me pull out my highlighter. Is from 5 to 6 here. From 5 to 6, we can see that this is a local minimum. Write this a little better, right? So we have a local minimum when x is equal to, let me make this a little better. F to now, but for similar reasons that we talked about before, we also have a local maximum as well that's included, but but it doesn't include the points 5 and 6. So first, I'll write this down and we can re-explain this. So we have a local maximum at x is equal to, well, not including 5 or 6. Because if you remember here, if we take this point 5 and we go a little bit here, that means that it can't be a maximum because, oh, there's a point higher than it, which is all the stuff going up here, right? And same can be said for point 6 because the second we go a little bit this way, we now have values higher over here. But if we grab any other point on this interval here, there's nothing else above it, there's nothing else below it, meaning that it can be considered a local maximum or minimum, right? So the best way to think about it when you see these straight parts, right, is that whenever you have a straight, like the straight part, and your function, its slope value is just 0, it can either be considered a local maximum or a local minimum, right? And then you have to look and see whether at those endpoints, whether it can be included or not included for a local maximum or minimum. But everything else in between will be a local maximum or minimum. And for that, that's actually everything that you need to know about graphing. Pretty simple if you just take a minute to think about it. Next, we're going to get into L'Hopital's rule, or however you say it. I still don't know. So, L'Hopital's. So pretty much this rule states when you have a limit problem, when you have a limit, right, and it gives you an indeterminate form, say 0 over 0, or you end up with infinity over infinity, or even 0 times infinity, or even infinity minus infinity, whatever weird form you get, right? What it tells you to do is keep on taking the derivative of your top and bottom function until you get a usable limit. So you just keep taking derivatives. This works especially well if you have functions where you can't manipulate it. Say you can't factor and cancel some stuff out, or you can't move around some terms or complete the square, or whatever technique you want to do. Whenever you can't do that, this is a very nice technique. So a good example of this is say we have the limit as x approaches infinity of x squared minus 4 over x squared minus 4x plus 3. Now, your first thought would be to try to factor this out, right? You factor it, you get x plus 2, x minus 2, all over x minus 1, x minus 3, and then you realize there is no other way you can go from here because there's no cancellation. So, using the L'Hopital's rule, what it states is now let's just start taking the derivative of the top and bottom, right? So what you're doing is the limit as x approaches infinity of d over dx of x squared minus 4 over d over dx x squared minus 4x plus 3, which then gives you 2x over 2x minus 4. And then you can see here, you can take the derivative once again. And this is just going to leave you with 2 over 2, which means that this function, its limit goes to infinity, x, you're going to approach 1. Pretty simple. Now, you can even do this with exponential functions and other stuff like that. So say we have the limit as x approaches infinity of x squared times e to the negative x. What I think here is that first we can rewrite this as x squared over e to the x, right? And then say you try to plug in, well, you can't plug in infinity, but try to put it in. You're not going to get anywhere, right? So we just rewrite this here real quick. We take the derivative of each side. So that's going to be 2x. And remember, our derivative of e to the x is just e to the x. And then we can take our limit again and see what happens. And then we end up with 2 over e to the x, which then now we know this because we know that if we put this in here, this is just going to be equal to 0. And now that pretty much covers everything that you need to know about L'Hopital's rule. It's pretty simple, pretty straightforward. Just keep on taking the derivatives of the top and bottom and see what value you're getting. Now, let's get into graphing. Here, oh, graphing. So, oh shoot. Let's say we have the function f of x, and it's going to be equal to x squared minus 4 over x squared minus 4x plus 3, right? Just like how we did before. First things first, we want to know some key things about our function. So one thing that's good to know is we want to know our x-intercepts. And our x-intercepts are going to be determined when our y value is equal to 0. So essentially, that's when is x squared minus 4 squared minus 4x plus 3, right? That's essentially just when your top is equal to 0, right? So it's just x squared minus 4 equal to 0, right? So that pretty much means we're just going to factor this out, and you get x plus 2, x minus 2 equal to 0. And so our x-intercept values are going to be -2 and 2, right? And so then we're going to want our y-intercept values. Our y-intercept values are when our x is equal to 0. So 0 squared minus 4 over 0 squared minus 4 times 0 plus 3. And then that just gives us a y value of -4 over 3 for our y-intercept. Then for our vertical asymptotes, what you have to remember is that your vertical asymptotes is when your function is going to be at 0 on your bottom. This here. Vertical asymptotes. This is going to be when our bottom part, x squared minus 4x plus 3 is going to equal 0. And so we just factor this out. So you get x minus 3, x minus 1, and then equals 0. And then you could just say our values for our vertical asymptotes are going to be when x is equal to 3 or 1. And then for horizontal asymptotes is when you, hold on, write this down here. Horizontal asymptotes is when you look at the power of your top and bottom. Write this here. Look at how slash bottom. So actually just put in our function again here. So we have x squared minus 4, and it was x squared minus 4x plus 3. So essentially what we look at is our highest degree part, and our highest degree part is going to be x squared over x squared, right? So we can say that a horizontal asymptote is just going to be at 1. But say that there was a coefficient here, and it was, say, 3x squared over x squared, x cubed x squared, their horizontal asymptote would be at 3, right? And so now we combine all this together, make a graph here. Oh, mine's a little wonky there. So I make it here, right? Let's number this up. Say 1, 2, 3, 4, 1, -2, -3, -4, 2, 3, 4, and then -1, -2, 2, 3, -4. Got that? Now, first off, you want to start drawing in your asymptotes. Let's put this in blue. And so well, actually, you can even put in your x and y intercepts first, but let's just start off with our vertical asymptotes. We know that these are going to be at 3 and 1. Well, we can put a nice little dotted line here, 1, and then at 3. And then we know our horizontal asymptote is going to be at 1. So we put a nice little dotted line here. And now we can start adding in our x and y intercepts. We know that our y-intercept is going to be at -4/3, right? So that's about 1 and a third-ish. So about here, somewhere about there. And then let's get in our x-intercepts. We know one of our x-intercepts is going to be at -2, and we know another one is going to be at 2. Now, where we go from here is we start plugging in a couple values to see what exactly is going on with our function around these points. So what we're going to do here is let's bring our function down here. Let's say bring down our x squared minus 4 over x squared minus 4x 3. So let's say we just plug in a 4 and see what happens. So 4 squared, that's 16 minus 4 over 4 squared, that's more 16 minus 4 times 4 is 16 plus 3. We look here, that is 12 over 3. All we need to know is that this is bigger than 1. We know that our function is going to be behaving somewhat like this, right? Because we know that we have these vertical and horizontal asymptotes here, so we know that it's going to be approaching these values from either side. And we were able to determine that it's up here because this number is greater than our horizontal asymptote 1. So it wasn't in the negative range, so it's going to be up there. Now let's analyze somewhere over here. But this one we already know because it's kind of given to us because of our y-intercept and our x-intercept here. We can tell that it's going to behave something. Oh, let me make this look better so it goes through it. Something like this. And then on the inside, we know that it's going to go through 2, right? But this one kind of does an interesting thing that's kind of counterintuitive because you would think because there's a horizontal asymptote, it's not going to cross this asymptote. But this one actually is going to behave like this, right? And so we can plug in some points and you could test and say, oh, it actually does behave like this. But an easy way to remember is that graphs, like functions like these, right? Where it's like these two polynomials divided by each other, they only have a couple set ways that they're going to look, right? So I'll draw a couple for example, like the one we just saw right now, or they could look like this and this, Or, let me erase here. You could end up with something like this, or you could end up with this here. You could end up with something like where you have something here, and then you have these vertical asymptotes here, here, and here, and then here, and then you have this one that kind of looks like a squared function over there, or you could grab this whole piece here and say you rotated it around and it was like this, you could have something like that. And then of course, like how we just saw before, where it's like where it's this little S shape in the middle. You could either have it the opposite way S shape, where it's like a little better. It's like this, or actually let me move this over. Say we got a asymptote here. Let's draw like how we have the one here, asymptote there. You can have the asymptote where the S curve is going like this, and then you have it here and then there. That's also a very valid function for that as well. So any of those things could happen when you have polynomials divided by polynomials like that and you're trying to graph it. And the easiest way to be able to graph it is to see those pattern recognitions and being able to understand it. And so with that, that covers everything that we need to know about what sections were we going over here. 5.1 to 5.5, Extrema's L'Hopital's rule in graphing. And so, to brief review, we went over extremas where we were able to figure out our global maximum, global minimums, and then we were able to spot these kind of interesting things that happens when the slope of our function is equal to 0. When finding our local maximum and local minimums, we're able to see where if we have a point that lies right on the edge between going up or going down, it can be considered, say for the case of the point 5, it is a local minimum, but it's not a local maximum. But on the range in between 5 and 6, not including 5 and 6, it can be a local maximum or a local minimum because there's nothing above or below it. And then we went over L'Hopital's rule, where we took the derivative of the top and bottom, and we kept on doing that in order to see what our function as it approaches infinity, what it tends to do. And then we were also able to do a little bit of graphing where we were able to identify our x-intercepts, y-intercepts, vertical asymptotes, horizontal asymptotes, and then be able to put that all together to form a graph. And with that, that's going to cover everything that you need